Good day everyone, and welcome to the fifth video in a series of videos illustrating the solution of the Delian problem, doubling the cube. In the fourth video, we demonstrated that the ratio of the geometric means x over y, where x is greater than y, is indeed the scaling factor when dilating or doubling the cube. In this video, we will show that the geometric means x and y seems to be the side lengths of the larger and smaller cubes. We will also show the modern algebraic solution for solving the doubling of the cube without using the double mean proportion. Alright, so I have prepared here a GeoGebra construction with a pair of similar cubes. We know that x is equal to cube root of a. Let's compute that by typing c is equal to 54, or a, raised to 1/3. So this is cube root of a, cube root of 54. We also know that y is equal to cube root of b. So let's compute that by typing d is equal to b raised to 1/3. So that would be 27 raised to 1/3. Cube root of 27 is 3. And now I will show you the connection between the side lengths and the geometric means. Please observe that these side lengths appear after reducing the ratio of the geometric means to its lowest term. So here's a GeoGebra app that I created where y is greater than x because b is greater than a. So my apologies. So let's find the side lengths of 54 and 27. So please observe. Alright, so C is our geometric mean, y, and then d is our geometric mean, x, where y is greater than x. Now let's extract the common factor from the geometric mean ratio. Okay, so c corresponds with e, okay, and then d corresponds with f. So we divide c by e. And we divide d by f. Now, let's reduce the ratio of the geometric means by dividing x and y by the common factor g or h. So, let's use g. So, we say and type c divided by g and d divided by g. What are we getting? Yes, you are correct. We are getting the side lengths. I is the side length of the bigger cube and j is the side length of the smaller cube. Hence, upon reducing the ratio of the geometric means to its lowest terms, we obtain the measurements of the side lengths. Now we're going to experience the modern method of deriving the ratio for the doubling the cube. This is a simplified approach without using the double mean proportion. Let us have our given definitions. So we have A, the volume of the smaller cube, and then S is the side length of the smaller cube. And then we have a relationship between the volume and the side length. The relationship of A and S is denoted by the equation A is equal to S cubed. Next, let's define B as the volume of the larger cube, where B is equal to 2A since we're doubling the cube, right? Again, S is the side length of the smaller cube. So the relationship of the volume of the bigger cube B and the side length of the smaller cube S is denoted by the equation B is equal to 2S cubed. Then we define T as the side of the larger cube, then we're going to solve for t. The relationship of t being the side length of the larger cube and the side of the smaller cube is denoted by the equation t cubed, so this is the volume of the bigger cube, is equal to 2s cubed. This is the volume of the bigger cube as well because we are doubling the volume of the smaller cube. So s cubed is the volume of the smaller cube, and we have 2 here. We multiply the volume of the smaller cube by 2 because we're doubling the cube. And that would be equal to t cubed because t is the side length of the larger cube. Right, so let's explain further the equation. So in finding the volume of the cube, we get the cube of the side length, right? So the side length is t, raise it to the power of 3. Then the volume of the larger cube is equal to 2a, twice the volume of the smaller cube. And yes, a is equal to s cubed. So we cube the side length s of the smaller cube. Alright, so now let's begin solving for t. We get the cube root of both sides. So we now have t is equal to cube root of 2s. Then finally, divide both sides by s. We now have the ratio t over s is equal to cube root of 2. This is the x over y ratio, right? Where x is greater than y. As a conclusion, the mystery behind doubling the cube is to find the factor, the ratio to use to multiply by the side length of the smaller cube, of the initial cube, in order to double the cube. And such ratio is equal to cube root of 2. Let's have a GeoGebra demo for our conclusion. So let's move the slider A to change the initial volume and see changes in x and y coordinates. So here, as we change the volume of the initial cube, the x and y coordinates change, and the x and y geometric means change. However, upon reducing the ratio of the geometric means to its lowest terms, we will obtain the corresponding side lengths of the similar cubes. Again, in doubling the cube, we have the fixed ratio x over y is equal to cube root of 2, where x is greater than y. And doubling the cube means multiplying the initial side length s by the ratio cube root of 2 to get the target side t. Let's have an example. Here is the side length of the smaller cube, the initial cube. So we say and type f times the ratio of the geometric means. That would be cube root of 2. So we say 2 raised to 1/3. What are we getting? Yes, we're getting the side length of the larger cube. Okay, here is the side length of the larger cube. So to get the volume of the larger cube, we simply raise k to the power of 3. We get the cube of the side length k. So 54 now is the volume of the target cube after doubling the cube with the initial volume of 27. Here's an important note. Cube root of 2 is an algebraic number, not a geometric number. When we say algebraic numbers, these are numbers that can be a root or solution of an algebraic equation. And then cube root of 2 is not geometric at all because we cannot construct such a magnitude using the classical straight edge and compass. Hence, we can say that there is a limitation on the classical straight edge and compass. Nevertheless, the Greeks did manage to evolve to algebraic solutions as a collective effort. Final expression here to get the target side t is equal to cube root of 2s. I would like to thank our dearest writer educators, Mr. Bondo, Mr. Villa, and Dr. Pawilan, for writing this beautiful book, History of Mathematics, that I am reviewing. This historical artifact serves as a beautiful inspiration to students like me. And thank you also to Rex Bookstore for printing such an inspiring book. And to all of you who have been watching my video lessons and reading my teaching documents, thank you so much. So this is Tutor Maan, and I hope that you have learned something